Thank you very much. As Brandon said, I'm Garrett Klunk, and today I'm going to be presenting a status update to an ongoing NASA Phase 2 STTR program between VSPAERO and the University of Illinois at Urbana-Champaign uh, concerning the development of an autonomous flight controller for a subscale distributed electric propulsion aircraft with a focus on how we are using Open VSP and VSPAERO to support validation and verification efforts under the program. With that, before we begin, I'd like to provide a brief review of the program background. So the goal of this NASA STTR Phase 2 is to develop a reconfigurable autonomous flight controller for a distributed electric propulsion aircraft, not only to provide lateral and longitudinal autonomous controls, but also to be reconfigurable in the event of failed propulsors. What's also unique about this is the propulsors themselves will be used as control effectors in addition to conventional aerodynamic control surfaces. And so the controller will reconfigure around propulsors that are inoperable to still maintain effective control. And what we'll be focusing on today is the comparison of our estimation of flight dynamics with OpenVSP and the system identified flight dynamics from our flight testing campaign of the subscale vehicle. On the VSPAERO side of things, last year, one of our engineers, Nick Brake, presented a status update on this program, detailing how we modeled our ducted propulsors in VSP, our development of a DEP array custom component to ease the modeling process of those propulsors geometrically, and our initial vehicle characterization, including propulsion airframe interactions using VSPAERO. And what we'll be talking primarily about today is our initial comparisons of those dynamics estimated in VSPAERO to flight test data and system identified flight dynamics. And with that, I will dive right into how we're modeling our aircraft dynamically and our comparison between VSPAERO and flight test. So to begin, we start off with standard textbook longitudinal and lateral directional aircraft dynamics systems of equations in 6 degrees of freedom motion. And they are presented here in state space form. We have a handful of stability and control derivatives for the baseline aircraft with control surfaces that can be estimated by use of VSPAERO and the automatic stability calculation subroutine within it. And for reference, I also provide our axis system, which will be relevant to keep in mind for later for positive forces, moments, and control surface deflections. From that baseline 6-DOF modeling, we also wanted to capture the influence of propulsors on the aircraft dynamics as well as control. So in order to do this, we characterized the propulsor used on the subscale flight test vehicle using Rotor to build a aero performance map. And essentially, we replicated the linearization process from VSPAERO manually using this flight test data. So we were interested in performing a linearization about difference in thrust. So using the Rotor data, we correlated that to a difference in RPM at our flight condition, and then use that delta in RPM to gather thrust and power coefficients from the propulsor data, and used those settings as inputs to the rotor disk element settings for the rotor disk components in VSPAERO. And what that allowed us to do is to run two different flight conditions to produce that delta, and then linearized forces and moments about those to get the stability derivatives, quote unquote, for the propulsors shown in green. What we also did was we assumed that there was going to be some propulsor dynamics in the physical response of the propulsor itself to its commanded signal. And we represented that with a first order transfer function based on prior efforts in the end of the phase 1 program and the very beginning of the phase 2. And from here, want to take a look at how we're using VSPAERO for this. So we started off by using the simplest solver, the vortex lattice method steady solver, with the geometry observed above. And for this, it was a really fast and computationally efficient method for generating aero forces and moments, and is generally effective for very simple planform geometries like our conventional Cirrus SR22 model. And it also had the benefit of being able to use that subroutine for calculating stability and control coefficients for using estimating derivatives. But while we were working on that, the Unsteady solver came out, and we decided that we also wanted to explore that for producing similar data sets, primarily because we were interested in what might have been a more representative propulsor behavior rather than the rotor disks used in the study solver. However, we quickly found out, due to the very high RPM of the propulsors compared against the very low velocity of the aircraft, it became a very slow and computationally heavy process. And we also required to do the manual linearization process across all states and control variables for our dynamics model using the Unsteady solver, because it's simply not built for that stability calculation subroutine. With all that in mind, our goal for looking into VSPAERO in the first place is to see whether or not this approach is sufficient for controller development in place of a high resource cost source of data, such as a flight testing campaign. Could you get close enough from the comfort of your own laptop? And so with that, it warrants an exploration of the data that we are comparing against. So what we're seeing here is a very high-level summary of what UIUC has done for supplying the system-identified data set for us to compare to. More details can be found in Aaron Perry's PhD dissertation, referenced in the bottom right of this slide for anybody who's interested. But as a brief overview, not only did UIUC perform a scope of flight testing with multi-orthogonal multi-sign maneuvers, exciting various dynamic frequencies of the flight test vehicle to generate a set of flight test data used in the system identification process to identify stability and control derivatives, but also performed a suite of wind tunnel testing of a subscale version of the subscale aircraft to look into general trends that we might expect in forces and moments from varying installed propulsor thrust. On the bottom left side of the slide, you can see a comparison of the raw flight test data shown in black traces and the reconstructed data, maneuver data from the system identified dynamics model produced from the system identification process. And in general, it is very close, but there are some differences that lead to some drifting in the response, which is typically expected and often requires a lot more training of the model to get more closely aligned. With that, I'd like to dive into the beginning of our comparisons of these models. So the first step in comparing the models is the model architecture itself. The system of equations that underpin the estimation methods between VSPAERO and system identification are largely similar but differ in important ways. The primary way in which they differ is the definition of propulsor contributions to the flight dynamics. As I mentioned before, with our VSPAERO approach, we are looking at differences in thrust input with a propulsor dynamics model included for an actuated response in the aircraft dynamics. But in the system identification model, the flight test data extracted from the flight test campaign really can only trace throttle input. It's very difficult to get beyond throttle from and connect the dots between throttle and thrust. So in addition to that, there are no propulsor dynamics included. There's an assumption that they may not be significant enough to warrant inclusion in the dynamics here. So those differences are hard to bridge across the gap. However, the set of pure aircraft dynamics highlighted in red should be directly comparable as they follow the same form. And in addition to looking at the models themselves, we have to reconcile the concept of what is actually happening when we linearize or attempt to linearize forces and moments between the two approaches. And this really was this probably is the largest takeaway from our work thus far, where in VSPAERO, you can set the vehicle to a specific trim flight condition and run analysis on that. And then if you want to look at how forces and moments change with a deflection of the elevator and positive elevator deflection as shown, you can do so while keeping the vehicle parametrically locked so that you're holding all other parameters constant, same airspeed, same angle of attack, etc. And this allows for a more decoupled analysis of each state and control parameter to narrow in on their specific contributions to dynamics. And this is most similar in the physical testing environment to a wind tunnel test on a fixed sting, where you can hold the vehicle in a flight condition and perform these tests. In the system identification side of things, even though the equations of motion which underpin the analysis are very similar, the vehicle is flying and therefore is able to react to perturbations of control effectors. So with our example, again, if you're at a trim flight condition and you deflect the elevator, you will have a very quick response which changes other state parameters such as airspeed, angle of attack, nose down pitch rate, and attitude, which will continue to change throughout time very quickly. And you find yourself in a different dynamic state um, than you were before. And that the challenge that introduces is when you have very similar terms, um, building out the equations of motion in state space form with different stability derivatives, it becomes difficult to determine whether the change in forces and moments should be attributed to the control deflection which you enacted or the immediate changes to the other states which followed from that. Um, so what this does is uh, kind of muddies the water from an apples to apples comparison to something different. And this is what we see when we examine each stability and control derivative in both of the models with our various approaches. So what you're seeing here is a visual representation of that comparison with scaled down versions of each stability and control parameter. This slide for longitudinal dynamics, comparing system identification results with error bars and vortex lattice method steady and unsteady approaches. And on the whole here, we see either outside of the assumed values with the gray boxes, we see either approximate matches or poor matches in the dynamic variables. And we can dive into some of these pretty quick. The first being force of in X due to air changes in airspeed. That's largely a drag estimate, and it is known in the VSP community that the vortex lattice method has within itself a very rudimentary estimate for parasite drag, and there are better ways to estimate that even within OpenVSP using the parasite drag tool to get a better idea of that characteristic. So that might help explain some of the differences there. The discussion I had in the last slide about how the vehicle reacts to changes in elevator deflection make themselves more relevant here with each of those derivatives, where not only are we seeing large differences in magnitude, but we're also seeing changes in sign between them, which very well could mean the difference between if this were used in an autonomous controller as the state estimator, it could mean the difference between a controller which stabilizes an aircraft and a controller which destabilizes it based on that sign convention, which is very important to note. And we also see instances where the system identification estimates are so close to zero that they're uncertain, the uncertainty bounds around them cross zero and could land on either side of positive or negative. And so with those, we're really not sure what we should be comparing against. But in those instances, tools like VSPAERO can help inform the end user of what side of the line perhaps they should be. And as we look at the lateral directional case, this is the same comparison just with the lateral directional dynamics. We see similar things pop up. We see a lot more instances where the uncertainty bounds on our system identification are wide enough to where we're not entirely sure what side of the sign they should be on. But again, VSPAERO can help inform what those should be. And I think it's most represented here with the Y-force with respect to elevator deflection, the fifth from the left. But outside of the other results, there's another which we point out, which is the yaw moment due to side slip derivative, which also doesn't match what system identification produces. And if you've been astute in the previous slide, you might have noticed that all of our VSPAERO simulations have been run without the fuselage included. And this is because while we modeled it early on, while we modeled it as accurately to the flight test vehicle as we could, we had some modeling troubles that were not easy to resolve with that geometry, and so we omitted them, believing that omitted the fuselage, believing that at the scale at which we were working with for this vehicle, we may not see a large effect on the overall dynamics anyway. However, on larger full-scale aircraft, it is well known that the fuselage provides a destabilizing effect on the N beta term specifically, which, if applied here, could bring the vortex lattice method estimates down towards where the system identification method prescribes it probably should be. So there are some conclusions about how we're modeling the aircraft in OpenVSP and VSPAERO, which system identification can shed some light on as well. But again, this is all fairly work in progress. So a summary of our key takeaways here of our current progress is that most of the VSPAERO stability and control derivatives that we've seen do appear within similar orders of magnitude of identified derivatives, even if they're not exact matches. A lot of them are approximate matches in that way, which is fairly encouraging and suggests that while it suggests that those estimates can likely be used for static and dynamic stability analysis at the conceptual design level within similar orders of magnitude, where your estimates are approximate and quick results are desired for quick iteration on designs. However, the differences that we do observe may come from the fundamental differences in how the flight conditions are modeled between the two approaches, whether they're fixed and allow single perturbations or single perturbations affecting a dynamic response, such as in flight. Those may contribute to a lot of the differences we're seeing in the stability and control derivatives, and may limit the use case for VSPAERO for controller development as a result. And we also, for our specific use case, found that the Unsteady solver in VSPAERO might not be an ideal tool for us to pursue stability and control derivative estimation for. As I had mentioned before, the vast difference in the RPM of our propulsors against the relatively slow airspeed makes makes an unsteady solution for which encapsulates a fully developed wake over the entire vehicle geometry, really time consuming, on the order of days. And on top of that, having to run a case to perform manual linearizations about each state and control parameter make that a very time-consuming process. However, that's not to knock the tool for anything. It may not just be designed for that purpose. It has its uses, but for something this time-consuming, it may not be appropriate. And from that, we have some next steps that we really need to address for our work. The first of which being to reintroduce the fuselage back into the analysis, maybe with a simpler geometry that represents the general shape of the fuselage, to see if we can correct some of those derivatives that are known to have notable effects from the fuselage itself. And then while we say that the Unsteady solver might not be ideal for a full stability and controls analysis, we can still look at point cases by running a fully developed unsteady case at the baseline trim condition to compare results from steady and unsteady and what that might tell us for our accuracy there, and provide a more complete comparison of relative performance versus resource cost. We also want to take a look at the VSPAERO and system identification estimates for propulsion airframe interactions and their effects. This may require converging the underlying dynamics models between the two approaches around propulsor parameters that can be tracked between both methods. The challenge being how we connect installed thrust on the flight vehicle to throttle, which is something that we can directly measure, and how we navigate that gap. And then, of course, a more traditional comparison of the dynamics models as they're all built up in subjecting them in an environment like Simulink to specific input maneuvers and assessing their response traces to see, the comparison that we've done so far has been great for giving an indication of what specific derivatives are comparable versus not, but it doesn't give a great idea of how different parameters, I guess, how sensitive they are to those differences, how much of a difference matters for a vehicle like this. So those being our next steps, at this point, I would like to thank you for listening in on my presentation and open the floor for any questions.
Great, thanks, Garrett. Looking at the live stream and the conference IO session, doesn't look like anyone has anything at the moment, but everyone listening in, please feel free to ask now if you have any. Otherwise, great presentation, and thank you for sharing.
Yeah, I really appreciate the time, Garrett, and it's good to see some of the work going on in my alma mater. So for everyone listening in online, we've got about 3 minutes until Justin starts with his presentation on building the OpenVSP program from the source code. So we are going to take a very brief break and then
Hold on
come
just
back.
a second, Brandon.
Oh, hang on. There's Rob.
I have a question.
Certainly.
Thanks, Garrett, for the talk. I think you make a really good observation about the discrepancy in timescales between what it takes to resolve an actual rotating propeller versus the dynamics of an airplane. And I've seen this also, well, I'm just talking in terms of computational cost, yeah. And then I've seen this also when people think that they're going to model a tilt weighing through transition from start of transition to end, but then resolving time accurate rotating blades the entire time. And you just think about that, a transition from beginning to end of a VTOL vehicle may take a minute. And if your props are at, several hundred RPM, then you're going to need to model several hundred revolutions to model that transition. And usually when you look at someone running, say, a full-on CFD, and they're doing a rotating rotor and time accurate analysis, they consider it a really big deal if they do 10 revolutions. So there is a fundamental, difference in time scales that you have to look at. And from the aircraft dynamics standpoint, the propellers really are a time averaged actuator disk kind of thing when you're looking at the rates of even short period and phugoid. And so you need tools that are mixed. And this is that's a question, clearly. The only other thing I'll add is that Dave Kinney's working on this. One of the things that's on his list, hopefully to do soon, is he's trying some even more simplified ways of modeling the rotating blades that will hopefully allow much faster modeling that would be appropriate, much closer to being appropriate for the aircraft dynamics type timescale.
Right, and we've been in contact with Dave about that specifically while we've been navigating, exploring the Unsteady solver, and I think this particular case highlights the importance of a tool like that to kind of bridge the gap between something that is really fast and computationally efficient and something that could really blow up in time scale, like you mentioned.